Welcome to our Science Brief. Today, we're delving into the fascinating world of slow slip events, often called silent earthquakes. Imagine an earthquake, but instead of a sudden, violent shake, the ground moves incredibly slowly, over days, weeks, months, or even years. This movement is so gradual it doesn't generate seismic waves we can feel, or that traditional seismographs easily pick up. So, how do we even know these silent events are happening? The key is precise geodetic monitoring. Scientists use tools like global navigation satellite systems, including GPS, which track tiny shifts in the ground's position, sometimes just millimeters. Satellite-based InSAR compares radar images taken at different times to map ground deformation over vast areas. On the ground, or in boreholes, tilt meters and strain meters detect subtle changes in ground tilt or strain. And for those elusive events under the ocean, seafloor pressure sensors and developing fiber optic systems help us monitor vertical deformation of the seafloor, which is crucial as many large earthquakes originate offshore. Now, what's the connection between these slow slip events and the earthquake hazards we worry about? It's a complex picture. Slow slips redistribute stress on faults. As one part of a fault slips slowly, it can actually increase stress on locked sections nearby, potentially pushing them closer to a major rupture. Conversely, they might also release built-up strain, possibly reducing earthquake likelihood in that spot. Some research even suggests that slow slip events occurring shortly before large earthquakes might have played a role in initiating them. These events also help scientists map out which parts of a fault are locked and accumulating strain, versus those that are creeping or releasing strain slowly. This is vital information for estimating the potential size of future earthquakes. Often, slow slips happen at the transition zones between these locked and creeping areas. Sometimes, they're even accompanied by swarms of small earthquakes, indicating an interplay between slow and fast slip processes. While a single slow slip event isn't a reliable predictor of an imminent large earthquake, many occur without a major tremor following. Their cumulative effect over time significantly alters the strain on a fault. Continuous monitoring, combined with other data, could improve long-term earthquake hazard assessments. It's important to remember, though, that these slow slip events themselves don't cause destructive shaking, despite sometimes having equivalent magnitudes to damaging earthquakes, simply because their energy release is so slow. Research in this field is advancing rapidly. Scientists are compiling global datasets, and statistical analysis shows earthquake rates can increase near slow slip events. Machine learning and AI are being used to better detect and characterize these subtle movements. Sophisticated computer models are helping us understand the physics involved, including how factors like fluid migration and fault friction contribute to slow slip. Plus, new and more sensitive observation technologies are being developed, especially for challenging offshore environments. We're learning that slow slip is part of a whole spectrum of fault behaviors, from gentle creep to catastrophic earthquakes. In conclusion, the study of slow slip events, driven by these advanced monitoring techniques, is revolutionizing how we understand earthquake processes. While they don't directly cause shaking damage, their role in transferring stress and interacting with potentially large, damaging earthquakes makes them a vital component of modern seismic hazard assessment. Continued research is key to unraveling the mysteries of these silent tremors and improving our ability to forecast and mitigate earthquake risks.